Now, as many of you have picked up on these videos, if you watched enough of them, I'm actually a chemical engineer. My BS is in chemistry, my BS is in chemical engineering, but my PhD is solidly in engineering. And while I really do enjoy chemistry, I love it, sometimes chemists do things that just get under my skin. And one of them is how they name the particular reaction we're looking at. So we talked about allylic hydrogens in a previous video, and we talked about how they are stabilized by resonance. And that's a pretty cool concept. I love that because that's a good application of chemistry, like showing how resonance increases stability. But let's say we have more than one double bond involved. So let's say we have a whole bunch of conjugated double bonds. And we want to do bromine plus light. And our first step in this reaction is that we're going to create a bromine radical. And the bromine radical is going to extract a hydrogen to give us HBr in this radical. Now, this radical is stabilized through resonance. So if we were to draw a resonance structure, we would get this. But here's the thing, we have another double bond here, so what can we resonate with that? Well, of course, as long as we can draw a resonance structure, we can do it. So there are actually three structures we can draw with the radical. Now I realize this is just this turned around. We're going to keep it simple. If you want me to make it a little bit more obvious, here, I'll put a methyl group in there. But what's going on here? Well, we can actually move a radical along a chain. And so actually when we do this reaction, we have three potential products. The first is going to be the immediate one. We form the radical and then immediately the bromine attacks it. And we get this molecule. The second is that the bromine can attach to that radical. And the last is that we can get bromine attaching to this one. So, first of all, which one is most likely to occur? So take a guess, pause the video, take a guess, come back. My answer is that this is going to be the predominant product. And the reason it's going to be the predominant product is that in this case we have two primary radicals and we have a secondary radical here. So while we are resonating, resonance is going to favor the more stable configuration. It goes through all configurations, but this is going to be the one that occurs most likely. And so we end up forming this one here. Now, that is what you'd expect from thermodynamics. Here's how we're going to make this super complicated, and this is what drives me up the wall about chemists. There's the kinetic versus the thermodynamic product. The kinetic product is the first one here. And that I'll agree with. It is the kinetic because it is the fastest. If you form a radical and you don't give it time to resonate, you would make this in preponderance. And so to favor the formation of this, we would go to low temperatures because there is an activation barrier associated with moving this double bond along. So if we do this reaction at low temperatures, we will get what's called the kinetic product. Here's the misleading one. These are what's considered the thermodynamic products. So why do they call it a thermodynamic product? Because if you have heat, they're accessible. That is not what thermodynamic means, but they tried, right? So our thermodynamic products are the ones we favor at higher temperatures because we have supplied enough energy to let this resonance happen. There is enough energy to jump over the activation barriers and go back and forth. So we would call these two end products the thermodynamic products simply because if we supply heat, thermo, the dynamics will drive us to them. Why does that irk me? The true thermodynamic product is this one. This is the one that is favored most by thermodynamics. So, thermodynamic product does not mean it is the most stable product. It means it is a product that is accessible at higher temperatures. The kinetic product is the one that you favor at low temperatures, which occurs the fastest. And it occurs the fastest because it's the simplest. There's no intermediate resonance and moving around the double bonds in order to make it happen. Now, at any temperature, you're going to get a mixture of all three. At low temperatures, you're going to favor the kinetic one where there's no movement of this radical along the bond. And at high temperatures, you're going to favor these where there's enough energy to get over those activation barriers. You will end up with a thermodynamic mixture, meaning a mixture that favors the most stable one versus, you know, the least stable one being the smallest quantities. Now, this is true if we form any mechanism, we go through any mechanism which permits us to form something that does a resonance structure. So let's say we replaced this radical with an OH, and we did HBr. Well, in this case, we're no longer forming a radical, we're forming a carbocation, and carbocations are going to act the exact same way. They move along by resonance, and if we go to low temperatures, we're going to favor substitution at the initial point of attack, or at high temperatures, we favor the thermodynamic products, which of those are accessible by resonance. So, thermodynamic versus kinetic. Kinetic, low temperatures, it's the simplest one. Thermodynamic products are those that are done at high temperatures because they're given enough energy to allow resonance to occur to let our radicals and carbocations move along.